Hi, in this video, we are going to begin our section on number theory for the course. So the first thing that we look at is exact division. So what is exact division? So let's say let A and B be integers with B not equal to 0, not equal to 0. If there exists, if there exists an integer C such that A is equal to BC, A is equal to BC, then we say that B divides A exactly. So this is the notation for B divides A. If there is no such integer C such that A is equal to BC, we will say that B does not divide A. This means B does not divide A, right? Now, the first thing that we look at as a property for this exact division is the property of transitivity. So it is transitive in nature. What does that mean? If B divides C and C divides A, it implies that B divides A. That is the transitive property of exact division. Then we also know that if A, B, C are integers and if B divides A and B divides C, then B will divide any combination of A and C, any linear combination of A and C. So A plus minus C will be divided by B. So this is saying that integers that are multiples of B are closed under addition and subtraction. What does that mean? Basically, if you take any multiples of B, no matter how you combine them, the resulting integer will also be divisible by B. So that is the second property. Then the third one is let A and B be integers. If A and B are integers, if B divides A, then either A is 0 or mod of A must be greater than equal to mod of B. So if B completely divides A, that means A is divisible by B, then A should have a larger modulus than B. Mod of A should be greater than equal to mod of B. And if that is not true, then A must be the number 0, because 0 is always divisible by any other integer. So this is a very important property because we'll be using this property to sometimes prove that two numbers are equal. In number theory, you might need to prove situations where A is equal to B. So we'll say one way to prove that A is equal to B is if A divides B and B divides A. It implies that mod A must be equal to mod B, right? Because from here, mod B should be greater than mod A, and from here, mod A should be greater than mod B. Both the things can be true only if both the numbers have same modulus, right? Okay, let's look at another property here, or actually a problem solving tactic. So we'll say sometimes you have to prove something like B divides A is difficult to prove. You have to prove B divides A, but it is difficult to prove. Then a common strategy is to try to get an intermediate number C. So if we can show that there is a C such that B divides C and C divides A, we can take advantage of the property of transitivity to prove that B divides A. So direct proof may be difficult sometimes, and you might need to take into account an intermediate, right? Okay. Now, if we need to show B divides the sum of these numbers, A1 plus A2 till AN, then sometimes it is more convenient to try to prove that B divides AI for I equal to 1 to N. So it might be more convenient to prove the stronger proposition that B divides each of these numbers. If B will divide each of these numbers, so because multiples of those numbers will be closed under division, therefore the combination of those multiples will also be divisible by B. This is a stronger proposition. It is not necessary that B should divide each of these numbers in order to divide the sum of these numbers. For example, 3 divides 1 plus 2, but 3 does not divide 1 or does not divide 2, right? So it is possible that you have other situations, but sometimes it is useful to try to prove the stronger condition, right? Finally, we can state another implication. If an integer a is not equal to 0 and mod a is less than mod b, then b does not divide a. So this is using property number 3. What we are doing is a is an integer that is non-zero and the modulus of a is less than mod b, then obviously b cannot divide a, right? This is the converse of the property 3. Similarly, if b divides a and mod a is less than mod b, that guarantees that a must be 0, right? B is a divisor of a and mod a is less than mod b somehow. That cannot happen except in the case that a is 0. So that is some standard properties of exact division. Now we look at the next thing, which is division with remainders. Division with remainders. Okay, so what is the standard theory here? If a and b are integers and b is greater than 0, then there exists integers q and r, integers q and r such that a is equal to bq plus r, where r is from 0 is less than r is less than b. This is the condition on r. Here r is called the remainder and q is called the quotient. Q is called the quotient upon dividing a by b, right? Now, this representation of a in terms of b and r is always a unique representation, is unique. And we can prove that there is a proof of the uniqueness of this representation. We can say that if there are two ways to do this, for example, if a is equal to bq plus r and a is equal to bq1 plus r1, where q1 and r1 are two different integers, such that 0 is less than r1 is less than b also, then we can subtract these two equations and get 0 is equal to bq minus q1 plus r minus r1, or that implies that b times q minus q1 is equal to r1 minus r. So this means that b divides r1 minus r, right? Now we know that both r and r1 are less than b. So obviously mod of r minus r1 is less than mod b. So therefore this implies that r1 minus r must be equal to 0. And if r1 minus r is equal to 0, r1 is equal to r. And if r1 is equal to r, then q is also equal to q1. So basically we are saying that there cannot be two different representations when you divide a and b, a by b, right? You will get only a single quotient and a single remainder. This is a unique representation. And we are using the fact that b divides r1 minus r and r1 minus r mod is less than b implies that r1 minus r must be 0. This is one of the properties that we discussed just now. Okay, now one way to write the quotient here, where q was the quotient, and if r is 0, we say that a is divisible by b. A is divisible by b. And the Q quotient's value is actually the GIF of A by B. So we had A was equal to BQ plus R, and the value of the coefficient or the quotient Q is the greatest integer less than equal to A by B, right? So this fact is sometimes very useful in problems. So keep that in mind. The next topic that we look at in the section here is called GCD. And I know you guys are all familiar with the idea of GCD. So I will quickly describe the definition. So let's say let A1, A2 till AN be integers that are not all zeros. Integers that are not all zeros. An integer, for example, plus minus 1, that can exactly divide all of these A1 to AN, all of the AIs where I goes from 1 to N is known as a common divisor, for the set. The common divisor for the set A1, A2 till AN. Now, a non-zero integer can only have a finite number of divisors. A non-zero integer can only have a finite number of divisors. Why is that true? Because if my integer is A and divisor is B, we know that mod B is less than equal to mod A, right? So since mod B is less than equal to mod A, the number of integers will be finite, right? B values can be from minus A till A. So the number of integers will be less than or equal to 2A plus 1, right? So any non-zero integer can only have a finite number of divisors. So therefore, all of these integers will have total of a finite number of common divisors. Finite number of common divisors are possible because it is taking some divisors which are common from a finite set of divisors. So it will be a finite number of common divisors, and any finite number of integers will have a maxima or a minima. So we can find from here the maximum value of the common divisor, right? That number is known as your GCD. The largest common divisor is known as the great GCD. So the notation for GCD, usually we write GCD of these numbers using the symbol, we put it in a bracket and we separate the numbers by commas. So this is the symbol for GCD of A1, A2 till AN, right? Okay. So let's look at some properties of this GCD. So the first thing is, if D is a common divisor of A1, A2, AN, right? Then minus D is also a common divisor. Obviously, division can be done with both negatives and positive divisors. If D is a common divisor, minus D will also be a common divisor. And this tells us that the greatest common divisor will always be positive. Among the set of common divisors, there will be several values. The negatives of those will also be there, but the greatest value will always be a positive value, right? GCD will always be positive. The next property is, if GCD of A1, A2, AN is equal to 1, this symbol basically means GCD of these numbers is 1. Then we say that A1, A2, AN are relatively prime to each other or co-prime. Relatively prime or co-prime. Now, there is another idea of uh, being prime to each other. You could also have if any two numbers in this set a1, a2 till an are relatively prime. If any two numbers, not the entire set, but any two numbers in the set are relatively prime, then we say that the whole set is pairwise coprime. What does pairwise coprime mean? It means we can pick any two numbers out of the set and those two numbers will also be relatively prime. Like there is a difference between relatively prime and pairwise coprime. So the difference is that you could be relatively prime, but you do not have to be pairwise coprime. But if you are pairwise coprime, then you are definitely relatively prime also, right? So that is an obvious statement. If you think about it, you should realize. Now, one thing to add here is that if A1, A2, GCD is 1, then we can say that the only common divisors for these integers are plus or minus 1. These are the only common divisors. Okay, let's look at the next property, property C. We say that let A and B be integers and B is greater than 0 and B divides A. Then the GCD of A and B will be equal to B. So B completely divides A. So the common divisor of A and B could be numbers smaller than B or could be B itself, right? So the greatest common divisor is obviously B. Okay. The next one is we can show that in general GCD of AB will be equal to GCD of A plus B by comma B will also be equal to GCD of A plus BQ comma B for any integer Q. For any integer Q. So how do we show that? So we will say, we'll try to prove this. So let's say D is equal to the GCD of A and B and D dash is equal to GCD of A plus B comma B, right? Now from here we know that D divides A and D divides B, right? So from here, from the fact that D divides both of them, so D should divide A plus B, right? So D divides A plus B now, and we know that D already divides B. So this implies that D is a common divisor of A plus B and B, right? So what was the greatest common divisor of A plus B and B? That was D dash, right? So from here we can say that D must be less than equal to D dash, right? This is obvious. Similarly, working from here, we can say that D divides A plus B and D dash divides A plus B and D dash divides B. So that implies that D dash divides A, because we can subtract these two numbers and we'll get D dash should divide A. So now we're getting that D dash is a common divisor of A and B. Common divisor of A and B, which implies that D dash should be less than the greatest common divisor of A and B, which is D. So from here we are getting D dash is less than D. And these two combined imply that D must be equal to D dash, right? So this is a very simple proof of the fact that if you have GCD of A and B, it is the same as the GCD of A plus B comma B. And we can similarly show that any combination A plus B times Q comma B, the GCD of that is also same as GCD of A and B, right? Now we come to the very important section for this chapter, which is the Euclidean algorithm. This is an algorithm to find the GCD of two numbers. So let A and B be integers and d is greater than 0. Now, if you divide a by b, a divided by b, basically we can write a is equal to b q naught plus r naught, where 0 is less than r naught is less than b, right? Now, what we can do, the next step, we can divide b with the remainder that came here, right? So we can say b divided by r naught. So that will become b is equal to r naught times q1 plus r1, right? Here 0 is less than equal to r1 is less than r naught. And similarly, in a chain, we can keep doing this. The next time you would have divided r naught with r1, and you would have gotten a q2 and an r2, and so on. You keep doing, you will get rn minus 2 should be equal to rn minus 1 qn plus rn. And finally, we might have that rn minus 1 is completely divisible by rn. So rn minus 1 is rn times qn plus 1. And here the remainder is 0, right? So the remainder becomes 0 in this last step. So we can show that if you do this sequence of divisions, always the GCD of A and B, the GCD of A and B is equal to the GCD in each step, B and R naught, is equal to the GCD of R naught and R1. And finally, at the end, you'll get it is equal to the GCD of Rn minus 1 Rn, but Rn minus 1 is completely divisible by Rn, so that is equal to Rn. What was this Rn? Rn was the last non-zero remainder in this sequence, last non-zero remainder in the sequence in these successive divisions, right? Successive divisions. Now, how can we show these steps? GCD of A and B is equal to this. So basically, A can be written as BQ plus R naught, right? So since when we take GCD of A and B and we divide A with R, so we get A is BQ, A with B, we get BQ naught plus R naught. So this is the same as saying GCD of BQ naught plus R naught, comma B, right? And from the previous point that we discussed, we knew that A plus B comma B GCD or A plus BQ comma B GCD is the same as AB's GCD, right? So here you have, think of this as your A plus BQ naught comma B GCD will be equal to AB's GCD, which will be R naught comma B. So now we have reduced the problem from the GCD of A and B to a smaller number, the remainder and B. And after that, now I'll divide B with the R naught. So B is a bigger number and B will be written as basically R naught Q plus R1 comma R naught. And that will be equal to the GCD of R1 and R naught. So this is the sequence of divisions which reduces the problem from a large one to a smaller one, right? And slowly it will terminate at some point, and at some point you'll get a zero remainder. So the last non-zero remainder will be your GCD, right? Now, this also implies a very important idea that the GCD of A and B can be written as GCD on A and B is also equal to AX plus BY, where X and Y are integers. The GCD of A and B will always be expressed in this form, AX plus BY, where X and Y are some integers. How do we get this representation? You have to look through the series of successive divisions that we did and work backwards, work in reverse from the last step and keep substituting terms forward. And you should be able to eventually prove that any GCD of A and B can be written as AX and BY, AX plus BY. For example, let's take the case of GCD of 36 and 8, right? So the first step was what? We divide 36 with 8 we will get a remainder of 4. So you would get 4 is the remainder. So the next step is 8y with 4. And then you would get a non-zero remainder, right? Basically, when you divide this, you get 4 and 0, right? So we can easily see from here that 4 is the GCD, right? The last non-zero remainder is 4, right? But we can write it like this: 36 is equal to 8 into 4 plus 4, and then 8 is equal to 4 into 2 plus 0, right? So this was the step here. So GCD was 4, the last non-zero remainder. So we can always write F4 as 36 minus 8 into 4, which is 1 times 36 plus minus 4 times 8, which is in the form GCD of A and B is equal to X times A plus Y times B. Here X is 1 and Y is minus 4. Obviously, if there is a longer chain, you will have to do this step many times to get the final situation, right? But it is true that anytime you have GCD of two numbers, it can always be represented as AX plus BY, right? Where X and Y are any integers, some integers. The next property is two integers A and B are co-prime if and only if there exist integers X and Y such that AX plus BY equal to 1. Now, this is a direct application of the previous property. We said that always GCD of AB can be written as AX plus BY. But now in this case, since they are co-prime, this must be equal to 1. So we are getting this must happen for two integers to be co-prime. Now, if X and Y make AX plus BY equal to 1, then it implies that AB, GCD of A and B exactly divides the LHS of this equation, Why? Because the GCD of A and B divides A and GCD of A and B divides B. So it is dividing this term and it is dividing this term. So it should divide the combination of those two terms in under addition. So we know that GCD of A and B exactly divides the LHS of this equation, which implies that GCD of A and B should also divide 1, right? So from here we conclude that GCD of A and B must be equal to 1, right? So it is a co-prime situation happening here, right? Now the next property is any common divisor of A and B is a divisor of their GCD. So what is the meaning of this? Any common divisor of this will obviously be lesser than the GCD of A and B. So we are saying that any common divisor of A and B is a divisor of the GCD of A and B. This is important here. The next property like this is let M be a positive integer. Let M be a positive integer. Then we have M times the GCD of A and B is equal to the GCD of MA and MB. We'll be using this property also many times. So keep this in mind. M times the GCD of A and B is basically the GCD of MA and MB. So the next thing that I want to show you is let GCD of AB be equal to D GCD of AB is equal to D, then the GCD of A by D and B by D is equal to 1. Okay. So let's do the proof of the second property. So how do we prove this one? So let's say let D is the GCD of A and B, and let D dash be the GCD of MA and MB, right? So what we know is that D divides A and D divides B. So obviously MD will divide MA and MD will divide MB, right? So MD is a common divisor, of MA and MB. Now, if it is a common divisor of MA and MB, it must be smaller than the greatest common divisor of MA and MB, right? So we know that MD is smaller than or equal to D dash, right? And now we can do the reverse process also. So basically, we can say that D dash is the GCD of MA and MB. So if D dash is the GCD of MA and MB, we can find, okay, we can do it in a slightly different way. We can say that from the first relation here, we can write AX plus BY. There must be AX plus BY. X and Y are integers such that AX plus BY is equal to D. And now we also know that if you multiply both sides by M, MAX plus MBY should be equal to MD. So think about it. This means that we have MA times X plus MB times Y is equal to MD, which basically tells us that MD is GCD of MA and MB, right? But we had already gotten D dash was the GCD of MA and MB. So we have shown that MD must be equal to D dash, right? So MD must be equal to D dash. So D dash is this, and M times D is this, right? So hopefully you understood that we are able to prove that M times the GCD of A and B is equal to the GCD of MA and MB. Let's look at the next property. This is, let A and B be co-prime with M, then AB is also co-prime with M, is also co-prime with M. So basically, this property says that integers are co-prime with M are closed under multiplication. So if you have several integers that are all co-prime with M, then if you take the product of those integers, the product will also be co-prime with M. That is the idea here. So this property can be generalized to more than two integers as well. The next thing is a consequence here of this property. So suppose we know that B divides AC. If B is co-prime with C, basically that is the statement that GCD of B and C is 1. So it is co-prime with C. This implies that B must divide A. So the property is that B divides AC, right? But B and C have no common factors. So that means that B and A must have common factors, right? B must divide A. Otherwise, how will B divide AC? Right? So this is an obvious property. You can do a simple proof for this as well, but I will leave that to you. The next thing that we look at here, so we can actually show the proof for this. The proof of this, for example, is if BC is 1, we know that BX plus CY equal to 1. So that implies ABX plus ACY equal to A. And the LHS here, is a multiple of B. Why? Because B divides AB obviously, and B divides AC is given in the problem, right? So LHS is a multiple of B, therefore RHS is also a multiple of B. So B must divide A, right? That's a simple proof of this one. Similarly, you can prove all the other properties earlier that we have seen also. You use the definitions that we have so far established, and using those results, you can prove all of the properties that I'm showing you. So I will leave the rest to you. I don't want to spend too much time on these ones because these are quite easy. Now we look at the idea of least common multiple. Least common multiple. So what is the least common multiple? If you have A1, A2, AN, be non-zero integers, what we can do, a number that is a multiple, of all of these AIs is known as a common multiple. The least common multiple will be known as LCM. The least common multiple is written as LCM, and it is, the notation for that is square brackets A1, A2 till AN. Now, in the next section of the course, we'll discuss prime numbers, and there we will see some ways to classify LCM and GCD in different ways. But for now, we will say the following properties of LCM. So let M be an integer. A divides M and B divides M. So basically this means that M is a multiple of A and M is a multiple of B. So M is a common multiple, right? M is a common multiple of A and B. Multiple of A and B. So what is the least common multiple? So least common multiple is AB square brackets. So that will definitely divide M now. Because what we are saying here is any common multiple of A and B, any common multiple of A and B is a multiple of the LCM of A and B. That is the first idea. Then the next thing that we see is let M be an integer. M times the multiple or LCM of A and B is equal to the LCM of MA and MB. If M is any integer, M times the LCM of A and B is equal to the LCM of MA and MB. Okay. What is the next thing? This is a standard property that you see in lower grades also. We have the product of the GCD of A and B with the LCM of A and B is equal to the mod of A and B. Now here, if GCD of A and B is equal to 1, which means that A and B are co-prime, this property implies that the LCM of A and B will simply be equal to the mod of AB, the product of these two numbers. Okay. So this property can be generalized. So if you have multiple numbers A, B, C, D, and so on, which are all pairwise co-prime, these are all pairwise co-prime, then their LCM is the product of these numbers. LCM is simply the product of these numbers if they are pairwise co-prime. Okay. Now, two important results that you should know before we start doing some questions are these. This will be coming in handy many times. So if n is a positive integer, if n is a positive integer, then we can always say that x power n minus y power n can be factorized like this: x minus y, x power n minus 1 plus x power n minus 2y plus x power n minus 3y square, so on till x power 1 y power n minus 2 plus y power n minus 1. So this is the factorization of x power n minus y power n, and this is going to be super important. So this is true for any positive integer n. Notice that all the terms here have degree n minus 1, right? You can multiply it out and check the proof of this identity. The other identity that we'll be using is if n is a positive odd integer, if n is a positive odd integer, then x power n plus y power n can be factorized like this: x plus y, x power n minus 1 minus x power n minus 2y plus x power n minus 3y square, so on till minus x y power n minus 2 plus y power n minus 1. This is also an identity that will be useful. This is true only for odd integers. For example, x cube plus y cube, you are familiar with this identity: x plus y, x square minus xy plus y square. Similarly, we can write for x power 5 plus y power 5 using this identity. So keep these two in mind, because when we solve problems, you will be using this constantly. So let's start our discussion of problems. We have basically covered the theory for exact division. We saw divisibility, we saw Euclid's algorithm, we saw division with remainders and GCD and LCM. So that covers our section theoretically. Now let's look at a few problems. The first one is this one. Let fk be 2 power k plus 1 with k greater than equal to 0. We have to prove that if m is greater than n, then fn divides fm minus 2. Now, there are many ways to prove this. The smallest or shortest solution is basically think about 2 power m minus 1, and we can always factorize it in this way. So we can say that this is equal to 2 power 0 minus 1 multiplied by 2 power 0 plus 1 multiplied by 2 power 1 plus 1, and so on till 2 power m minus 1 plus 1. Why is this true? This is x minus y into x plus y. So the product here should be x square minus y square. So it will become 2 power 0 whole square minus 1. So that is actually simply 2 power 0 into 2 power 1. So that is 2 power 1 minus 1. So notice that you are getting this term, and you already have the conjugate term for that. This is becoming the new x minus y, and this is x plus y. So again, it will become, the combination of these will become 2 power 1 whole square minus 1, which will become 2 power 2 minus 1. And you are going to keep doing this repeatedly, and eventually you will end up with 2 power m minus 1 multiplied by this, which will give us this, right? Now, why did we do this? Because we can see that 2 power m minus 1, what is that? That is basically f of m, which would be 2 power m plus 1 minus 2. So the left hand side is f of m minus 2. And we are saying that this term is actually equal to 1, right? 2 power 0 minus 1 is actually 1. And this term, what is this term? This is f of 0, this is f of 1, and so on. This is f of m minus 1, right? So what we are getting basically from here is that f of m minus 2 is equal to 1 times f of 0 times f of 1 till f of m minus 1, right? And we know that from the problem that m was greater than n, right? So if m is greater than n, then among these different f's, right, there should be somewhere where f of n comes in, right? If m is greater than n, let's say this was 7 and this was 4. So you are going till m minus 1, right? So somewhere f of 6 would have come here, right? So f of n, which is f of 4 here, would have appeared in the sequence of f's, right? The idea is because m is greater than n, f of n appears in the sequence, and that just means that f of n divides f of m minus 2, right? So that completes our proof here. You can also do an alternative proof. I will just outline the first few steps and you should complete the proof after that. So in order to do an alternative proof for this, you can take x is equal to 2 power n plus 1 and y is equal to 1. And you should replace n with 2 power m minus n minus 1 in the formula x power n minus y power n is equal to x minus y, x power n minus 1 plus x power n minus 2y, and so on till x power y power n minus 2 plus y power n minus 1. So in this formula, take x as this, y as this, replace n with this. You will realize that the left hand side will become f of m minus 2. And you will be able to prove it. So try that out as well. We have already done one proof and I have shown you the next one, how to do it. Okay, let's go on to the next question. Question 2. Suppose n is greater than 1 is an odd number. Prove that n divides 1 plus half till 1 by n minus 1 multiplied by n minus 1 factorial. Right. So, correct. So what I would say here is this whole term can be split apart into many different terms. So for example, if you think about it, here n is odd. So the number of terms here is 1 to n minus 1. So the number of terms here inside the bracket is even number of terms in the bracket, right? Great. So you can group up two terms from here. We can always take pairs of two terms. One term is 1 by k and one term is 1 by n minus k, right? If you group up these two terms and multiply it with n minus 1 factorial, what happens? You will get on top n minus k plus k, which is n by k into n minus k, and multiplied by n minus 1 factorial, right? Okay, so that becomes basically n times n minus 1 factorial by k into n minus k, right? Now, obviously, when you did the grouping, we know that both k and n minus k are smaller than n minus 1, right? Why? Because k will appear somewhere inside this group, right? This group starts from 1 by 1, 1 by 2 till 1 by n minus 1. So both the terms k and n minus k are smaller than n minus 1 factorial, smaller than n minus 1. So obviously, then what we know for sure is that this will be an integer. Why is this an integer? because n minus 1 factorial is the product of all the integers from 1 till n minus 1. So it already has k and n minus k inside it. So that can be cancelled, right? The denominator can be completely cancelled, and this is an integer. So if this is an integer, what we know is that n divides 1 by k plus 1 by n minus k multiplied by n minus 1 factorial, right? Because this thing is coming as n times an integer, right? So n divides it, and obviously since n is odd, there is an even number of terms, and you can make groups of 2 like this, and n will divide each of those 2 groups, right? Each of those groups n will divide, so n will divide the overall thing as well. Obviously, I have not shown you all the steps, but the idea is pretty obvious. So I will leave the rest to you, right? The next one, let's look at the next problem. Suppose m and n are positive integers with m greater than 2. You have to prove that 2 power m minus 1 does not divide 2 power n plus 1. Okay. We have to show that 2 power n minus 1 does not divide this. So the first case is simple. If n is less than equal to m, then you can easily realize that 2 power n plus 1 will be less than equal to 2 power m minus 1 plus 1, because n is less than m, and which is less than 2 power m minus 1, right? So if n is less than m, I can show that the number here 2 power n plus 1 is less than 2 power m minus 1. Therefore 2 power m minus 1 cannot divide 2 power n plus 1, right? And this is all under the situation where m is greater than 2. So for example, if m is 3 and n is 2, it is obvious that 2 power 2 plus 1, which is 5, is less than equal to 2 power 3 minus 1, 7, right? So then we can say that 7 will not divide 5. So that case is pretty simple. We can establish the fact that the number is smaller. This number is bigger than this number, right? So we will work on the other case where n is greater than m. Let's say n is greater than m. So suppose n can be written as m times q plus r. Here we have divided n with m, and therefore 0 is less than equal to r is less than m, and q is greater than equal to 0. We have just done normal Euclidean division here, right? So then 2 power n plus 1 is equal to 2 power mq plus r plus 1, which is equal to 2 power mq multiplied by 2 power r. And instead of just writing a plus 1, I can add and subtract a 2 power r also, right? I can do this. I have added and subtracted a 2 power r so that I can factorize. So I will factorize it like this. It will be 2 power mq minus 1 times 2 power r plus 2 power r plus 1, right? Now we know that 2 power m minus 1 divides 2 power mq minus 1. Why do we know this? Because 2 power mq minus 1 is the same as 2 power m power q minus 1 power q, right? And this is like saying x power q minus y power q. Obviously, it can be written as x minus y into some integers, right? So we know that x minus y, which is 2 power m minus 1, will always divide 2 power mq minus 1, right? So this is known. So great. Now we know that 2 power m minus 1 divides this. Now we have to check that whether 2 power m minus 1 divides this or not, right? The remainder 2 power r plus 1. But it is obvious that 2 power m minus 1 does not divide 2 power r plus 1. Why? Because r was less than m. R was less than m, that means this number is smaller than this number. So the divisor itself is bigger, so it can't divide it. So therefore, we have seen that even though 2 power m minus 1 divides the first half of this, it doesn't divide the second half. So therefore, overall, 2 power m minus 1 cannot divide 2 power n plus 1, right? Which is what we wanted to show, right? Let's move on to the next question. Question 4. Here we have let n be a positive integer. Be a positive integer. The first part of the question is prove that GCD of 21n plus 4, 14n plus 3 is equal to 1. This was actually a question in the first IMO, 1957 or something. It's a very simple question. The proof is obvious because we can always write twice of 21n plus 4 minus 3 times 14n plus 3, right? Or vice versa. You can do 3 times 14n plus 3 minus 2 times 21n plus 4 is clearly equal to 1. So we have established ax plus by equal to 1, where x is 3 and b is minus 2, and a is 14n plus 3 and b is 21n plus 4. So that means that the GCD of a and b is equal to 1, which is what we wanted to show. So that was the simple first part. Let's look at the next part. The next part of the question says that prove that GCD of n factorial plus 1 and n plus 1 factorial plus 1 is also equal to 1, right? Okay. Here we can see a nice relation here. N plus 1 times n factorial plus 1 minus n plus 1 factorial plus 1. Think about it. Here this becomes n plus 1 factorial plus n plus 1 minus n plus 1 factorial minus 1, right? So this is equal to n, correct? So we are getting this relation n plus 1 times n factorial plus 1 minus n plus 1 factorial plus 1 equal to n. Now let's suppose that d is the GCD of n factorial plus 1 and n plus 1 factorial plus 1, right? Then d divides this term and d also divides this term. So d definitely divides the LHS. So therefore, d should divide n, right? Great. So since d divides n, we know d should divide n factorial, right? Correct. We are getting d is dividing n factorial, and here we already know that d divides n factorial plus 1, right? So we know two things now. D divides n factorial from here, and we know from here, from our assumption that d is GCD of this and this, so we know d divides n factorial plus 1. So if you subtract these two, this should mean that d divides 1, which means that d is equal to 1, right? So that is the proof that the GCD of these two is 1. We are using this identity. This equation is helping us figure this out, because from here we concluded that d divides n, and from there we know that d divides n factorial, right? Okay. The third part of this question is saying this. The third part of this question is let f of k be equal to 2 power k plus 1 with k greater than equal to 0. Prove that for m not equal to n, we have GCD of fm and fn is equal to 1. or basically any two numbers where m and n are not equal, any two numbers of this form are co-prime to each other, right? So we'll try to show this one. We have already proven a question earlier. From the previous example, we have shown that if m is greater than n, we know that Fn divides Fm minus 2. We showed that earlier. So that means there exists an integer, there exists an integer x such that Fn divides this. So Fm minus 2 is x times Fn, right? Fm minus 2 is x times Fn. So we can say that Fm plus x Fn is equal to 2. Obviously, this x and this x are different. I'm bringing both to one side. I'm saying x here is negative of this x, right? But integers could be negative and all, so that's fine. So we are getting this result. Because Fn divides Fn minus 2, we have an integer x such that Fm plus x times Fn is equal to 2, right? Now let's suppose D is equal to the GCD of Fm and Fn, right? So that means D divides Fm and D divides Fn. So from here, D should divide the combination of Fm and Fn, where x is an integer. So that means D completely divides the LHS, which implies that D divides 2, right? So if D divides 2, we know that D will be either 1 or 2. The only possibilities for D is 1 or 2. But now we notice that our Fk is always odd. Fk is always odd. So D cannot be 2. 2 cannot divide an odd number. Therefore, D must be equal to 1, right? So we are getting the proof by using the result from a previous example where we showed this, example 1, right? Once we use that, we are easily able to establish this. Okay. One last problem here. Let K be a positive odd number. Positive odd number. Prove that n into n plus 1 by 2 divides 1 power k plus 2 power k till the sum till n power k. Okay. So proving this is equivalent to showing that n into n plus 1 divides the product of 2 and 1 power k plus 2 power k till n power k, right? Now we know that since n and n plus 1 are co-prime with each other, are co-prime, we can divide the problem. We can divide the problem into two cases. Into proving that n divides 2 times 1 power k plus 2 power k till n power k, and n plus 1 divides 2 times 1 power k plus 2 power k till n power k. Only if these two things are true can we show that n plus 1, n times n plus 1 will divide the product of 2 and this sum of 1 power k, 2 power k. Now, because k is a positive odd number, right? We will use the identity that we had established earlier. X power n plus y power n is equal to x plus y into some stuff, integers, right? This is true for positive odd numbers. So now we can say that this is an odd number. So basically we can write this as, okay, I'll do it on the next screen. We need to show n divides 2 times 1 power k plus 2 power k till n power k. And this number is equal to 1 power k plus n minus 1 power k. This is one group. 2 power k plus n minus 2 power k. This is another group. And so on, till n minus 1 power k plus 1 power k, right? So basically 1 has appeared 2 times, n minus 1 has appeared 2 times. So we have handled all the terms 1 power k, 2 power k till n minus 1 power k. The only term we have not written is n power k. So we have a 2 n power k left over, right? So in this step, I have done nothing but rearrange the terms. I have arranged all these terms in groups of 2 and kept the 2 n power k outside, right? Now we know from our identity that x power k plus y power k is divisible by x plus y if k is odd. And in this question, k is odd. So therefore, this is divisible by n. N divides it. And here also n divides this. And all of these numbers, n will divide all of this, and n definitely divides this. So we have proved that n divides the product of this. So how did we prove that n divides the whole product? We are grouping it nicely and using this identity to show that n divides each of these groupings. So that establishes our entire thing. The next part of the problem is proving that n plus 1 divides it. Again, in a similar manner and a similar grouping, you can show that n plus 1 also divides it. So I'll leave that to you, and that concludes our discussion for this section, exact division. The next part of number theory that we'll look at is prime numbers, and that will be the subject of the next video. So I'll see you next time.